Section 9.5 is about the binomial theorem, and it has two objectives. The first one is to evaluate this new quantity that we're going to learn about with an n and a j, one on top of the other in parentheses. And the second objective is to use the binomial theorem. And this is basically a shortcut, so I love showing it to students because it can save you a lot of time later. So objective one is to evaluate this quantity n, j. And first we need to remember what a binomial is. So the bi, remember, is a prefix meaning two. So a binomial is a polynomial with two terms. So if you have something like x squared plus 4, y minus 3, those are binomials. What we're going to look at is what happens if you take something like x plus 2 to the power of 7. And with the exponent small, that's not that hard. If you want to do x plus 2 squared, you write x plus 2, and you write x plus 2 again. And then you do the FOIL method, plus 2x plus 2x plus 4, and combine your like terms to get x squared plus 4x plus 4. But then if I want to do x plus 2 cubed, I have to take what I got from squaring it and multiply it again by x plus 2. Well, now that's starting to get to be kind of a lot of work. I have to distribute the x and distribute the 2 and combine my like terms. So I'd really like to find a better way to do this when I have, say, x plus 2 to the 5th, because now we're starting to get to a lot of polynomial multiplication. So let's look for some patterns. First, let's look for patterns in the exponents. And what I notice is whatever the exponent on the binomial is, that is the same exponent on the first term and the last term. So when the exponent is 4 on the binomial, that's the exponent on the first term and the last term. And then let's notice some other patterns. So if I have x plus a, let's do to the 5th, we know we're going to have x to the 5th at the beginning and a to the 5th at the end. Well, now let's notice that the exponents on the x go x to the 5th, x to the 4th, x cubed, x squared, x, and then you could think of this as x to the 0, which is a 1, but we don't write that, but it makes it so the pattern is consistent. And then you could say, oh, there's an a to the 0 here, but that's a 1, so we don't write it. And then there's an a to the 1, which we don't write, exponents of 1, a squared, a cubed, a to the 4th, and a 5th. Then there's a number in front, and that's the last piece that we're going to talk about. That's called the coefficient. So if the exponent is 5, we'll say the exponents on the terms are x to the 5th, and then ax to the 4th, a squared x cubed, a cubed x squared, a to the 4th x, and a to the 5th. So those will be the exponents on the a's and the x's. And let's also know that when the exponent is 1, we get 2 terms. When the exponent is 2, we get 3 terms. When the exponent is 3, 4 terms, 1, 2, 3, 4. And when the exponent is 4, 5 terms. So we expect when the exponent is 5 that we'll get 6 terms. So notice that each term has a coefficient or a number multiplying it in the front. If you see 4x to the 7th, the 4 is the coefficient. So there's multipliers on these terms back in our example. So let's talk about how we find those. So the coefficients of the first and last terms are always 1 in these examples, but there's a shortcut way to generate the other coefficients, and it starts with Pascal's triangle. So Pascal's triangle starts with a triangle of 1s, and then there's always a 1 at the beginning, and then you add these two ones to get the middle term of 2. The next row is start with a 1, add the 1 and the 2 and get 3, the 2 and the 1 and get 3, and end with a 1. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Well, let's notice that the coefficients, when the exponent is 1, the coefficients are 1 and 1. So that's represented by this row in Pascal's triangle. When the coefficient is 2, the exponent is 2. The coefficients are 1, 2, 1. So that represents this row in Pascal's triangle. The next example, our coefficients are 1, 3, 3, 1. And we see that's 1, 3, 3, 1 in Pascal's triangle. So this 1, 3, 3, 1 came from x plus a cubed the 1, 4, 6, 4, 1 came from to the 4th power. This one is cubed. So these would be the coefficients if I had x plus a to the 5th power. So now we can write out all the terms. So we have 1 times x to the 5th plus 5 times a x to the 4th plus 10 a squared x cubed plus 10 a cubed x squared plus 5 a to the 4th x plus a to the 5th. So that's the expansion of x plus a to the 5th, and that's all there was to it. We didn't have to do some giant algebra. I see that I said x and wrote a, so let me fix that. There we go. Okay. So mathematicians discovered this pattern hundreds of years ago, and it turns out it has lots of applications. And when we write this quantity, we can read it as n choose j, and it turns out that n choose j will generate those numbers in the Pascal's triangle, so we don't have to draw Pascal's triangle every time we want to find those coefficients. So if we have n objects and we choose j each time, this combination will tell us how many ways we can do that. So when you're doing it in a calculator, it's doing n factorial over j factorial, then it's doing n minus j and doing that factorial and dividing. So 5 choose 3 would be 5 factorial over 3 factorial over 5 minus 3 factorial. So that's 5 times 4 times 3 times 2 times 1. Over 3 times 2 times 1. 5 minus 3 is 2, so times 2 times 1. So the 3, 2, 1 will cancel, and I'll end up with 5 times 4 is 20 divided by 2, so I get 10. So let's look back and see that 10 is the number that I get in the binomial expansion with the exponent of 5, so the n corresponds to the exponent in the binomial expansion, and the j corresponds to, this is the coefficient on the x to the 3rd power. So it's the 3rd coefficient. So the coefficients look like 5 choose 5, 5 choose 4, 5 choose 3, 5 choose 2, 5 choose 1, and then this is just a definitional thing, but 5 choose 0. So if you put these in your calculator, you can find the results by using the NCR button. So that's combinations. How many combinations can you make if you have n objects and you're choosing R at a time? So if you take elementary statistics, you study this a lot more, but we want to know how it's useful for us. So objective 2 is to use the binomial theorem And one other pattern I want you to notice is we have x to the 5th, and then we had ax to the 4th, a squared x cubed, a cubed x squared, a to the 4th x, and a to the 5th. I want you to notice that if I add the exponents, they always add up to this n number that's the exponent on the binomial that we're expanding. So this quantity is called a binomial coefficient. So if I expand x plus 3 to the 5, now I have a number for my a. So I'm going to have x to the 5th plus, and we expanded these earlier, but let's write it as 5 choose 5, then 5 choose 4 times our a now is a 3, x to the 4th, plus 5 choose 3, and our a now is a 3, x cubed, plus 5 choose 2, a is a 3, x squared, plus 5 choose 1, times 3 to the 4th x, plus, and we know the coefficient's always going to be a 1. You can write 5 choose 0 if you like, and then this is going to be the 3 to the 5th with no x. So 5 choose 5 is always going to be 1, so that's x to the 5th. And then let's see if we can tell what these are from Pascal's triangle. It was 5, 10, 10, 5, 1. So this is 5, 10, 10, 5, 1. But we need to do some simplifying. So we'll have 5 times 3 is 15x to the 4th. Plus 10 times 3 squared is 90, x cubed, plus 10 times 27 is 270x squared, plus 5 times 81 is 405x, plus 1215. So the only other thing we need to talk about is it doesn't have to be just a plain x. In this case, it's a 2x. But you just fill in all the blanks with 2x. So you put 2x to the 5th, plus we know this is a 5, times 2x to the 4th times 3, plus 10 times 2x cubed times 3 squared, plus 10 times 2x squared times 3 cubed, plus 5 times 2x times 3 to the 4th, plus 3 to the 5th. So that's how you can generate that binomial expanded to the 5th power that fast. Pretty cool, huh? So the other example here I have is with a negative number. And again, you just include the negative number in the parentheses then. So you have x to the 6th plus 5 times x to the 4th times negative 2 cubed, plus 10 times x cubed times negative 2 squared, plus 10 times x squared times negative 2 cubed, plus 5 times x times negative 2 to the 4th, plus negative 2 to the 5th power, and then you would simplify all those terms. So the usual test problem would be like numbers 29 to 32. So let's do this one in class so that we can practice together.